All right, welcome to the review session on Tuesday afternoon, March something. I don't know what it is, 24th, and we're all missing you terribly. I hope you enjoy watching this very dry video. Okay? All right, so what we're going to be working with today is me giving you a function that's already a rate of change. The function given to you is a rate of change. And they're going to come at you in the various formats. Velocity is one that we're going to start with, and then sort of general. So the first thing I want to do is just talk to you a little bit about units, as that's coming through, keeping up with what your units are, because this can be something that can help you decide what is it I need to do. Do I need to take a derivative? Do I need to take an antiderivative? Okay. So first of all, suppose I give you some function, and this is going to be written like it's going to have horrible things in it. It's going to have sine of this and ln of that and that. Some horrible stuff in it. But never mind what it says. Just note that the units are given to you. Make sure you know what they are. You saw I'm going to make this about dollars per minute. So whatever this function is, it's measuring how many dollars are changing per. Let me do hours since that's what I actually have on my paper. The answers will all make more sense. Okay. So this function, f of t, is a rate. It's dollars per hour. So even though there's no prime on it, even though it doesn't say f prime, it is a rate of change. And you know that by the units, dollars per hour, rate of change. Does everybody see? Yes? Okay, so if I take the derivative of this function, think about what the units of that will be. Okay? And it will be dollars per hour. How the dollars per hour are changing. Okay? Something is increasing by so many dollars per hour every hour. All right? If, on the other hand, I go backwards and I take the antiderivative of f of t, then my units are going to just be dollars. Okay? Do I have any questions about that? Okay. All right. So again, this original function does have a prime on it, but it is defined as a rate of change. Okay. And then f prime would be dollars per hour, and the antiderivative of f of t would be just in dollars. Okay. And the next thing you need to know is, what does this mean? Definite interval of a function. Specifically, when this function is a rate of change. Okay? A definite interval is an accumulator. It accumulates change, how much something changes. So when this function right here is a rate of change, and you do a definite integral, what that's going to give you is the amount of change. How much something has changed from A to B. Okay? And the units are going to be the same thing that they were up here on this. The units are going to be in dollars. So if you do an antiderivative of this and you get that the definite interval from A to B is 8, that means that whatever this represents has changed by $8. It's gone up by $8. If you get that this definite integral is -4, that means that the amount of change is -$4. It has gone down by $4. Does that make sense? Okay. What would this mean? It is, okay? This is the average value, okay? It's the average value of whatever's here. So the units of this are dollars. And the units here are going to be, this is dollars, and the units here is 1 over hours. Okay, so this is going to be in the same units that F is in, dollars per hour. getting a handle on these units is gonna be the thing that helps you when you read a problem and you go, what does it telling me? There's too much in here. And hanging on to these units can be the thing that really saves you on this, okay? So we're gonna walk through another one, another example with other examples of units, and then we're gonna do one with velocity acceleration and use that as sort of our starting point for these problems, okay? If I tell you that G of t is in gallons per minute, so if G of t is positive, then water is flowing into something. If G of t is negative, then water is flowing out. Something's increasing, something's decreasing, okay? So what would the units be if I take the derivative of gallons per minute? Gallons per minute. Now, physics people know that we sometimes say gallons per minute squared, but there's not anything intuitive about that. But when you say gallons per minute, every minute, okay? That's what that is. It'll sound a little bit better. Well, I don't know if that's better or not. Okay? Also, if we take the antiderivative of this, okay? If we take the antiderivative of this, it's going to simply give me gallons, okay? If this is a rate of change, right? That's a rate of change. All right? Like this says, the antiderivative or the definite integral from A to B of G of t, and this is a rate of change, which you can tell from its units. Then this definite integral is an accumulator of change. It tells you how much something has changed, the amount of change from A to B. Units on that will be, how much has it changed? That make sense? And then, I don't know, so don't forget this one. That is the average value of what? G. Of G. You want to know what the units are? What are the units of this? Gallons. What are the units of that? 1 over minutes. So what are the units of this? Gallons per minute. This is the average value of the rate of change, or the average rate of change. Okay? Average rate of change. Okay? Now we're going to do it with velocity and acceleration, because that's something that you all at least have some actual experience with. And we'll do meters per second. Right, so velocity in meters per second. Then v prime, take the derivative of the velocity. And never mind that we have another name for that. Skip a little space. It's going to be meters per second per second. There's that meters per second square thing, which y'all remember from freshman year, I'm sure, right? All remember from freshman year? Yes. And this, because it's velocity, has a special name. It is called acceleration. They don't all have special names like this one does, okay? But it is called acceleration. And if you go backwards, the antiderivative of velocity, then the units of that are going to just be meters. It's going to take you back to position or distance, depending on how you look at the problem. Okay? You're going to get meters. If I take the definite integral from A to B of the velocity, you're going to get an amount of change. Meters. And the word for this in physics is displacement. Okay, it's not distance. We talked about that before. You know, distance incorporates, if I walk this way 3 feet, and then I turn around and walk this way 3 feet, I've walked a distance of 6 feet, but my displacement is 0. So they're two different things. So this is displacement, how far away it is from where it started. Okay, and 1 over b minus a becomes the integral from a to b of the velocity is the average value of the velocity. And a lot of times people leave out that word value of. They just say average velocity. That means the average value of velocity. And so the units are going to be in meters per second. Okay? This is a new one. I haven't done this on one of the other ones. If I did this, just because it has a name, I'll do it. What is that going to be? It's going to be the average value of, or the average acceleration. And the units on this would be meters per second. Per second. Okay? So it's kind of using units to help you figure some things out. Okay? All right. Second. My favorite, absolute favorite thing in the world, so we'll start with that.
Is this still zero as unit?
Yeah, this is about this antiderivatives or integrals of rates. Okay, units was one part of it. This is another one part of it. Okay. Everything that I'm going to say now I have said before, but some of it I haven't stressed and we haven't necessarily had a question on it. So we just need to get this firm, and this is a good place to do it. If I know this to be true, then what's the antiderivative of big F of X? Little s. And plus c. Okay? You leave that constant of integration off when you're supposed to have it, and you're going to be in trouble. Okay? Well, you're going to lose one whole thing. Okay. Also, if I do the definite integral of big F, then what do I get? Little f evaluated at
E minus
minus little f evaluated at a. We wrote this down a long time ago, and then we sort of switched to that notation where we did this. Yes, but this was one of the first things we wrote down. And I just want you to look at that, see how that connects to the thing I told you a minute ago. This is an amount of change. Where did I end minus where did I begin? It is an amount of change. So if I ever ask you to find an amount of change, how much did it change? You're probably looking at a definite integral, okay? How much did something change? All right? This is the change in F, in little f, from A to B. Okay? And then this is the big one, this one right here. This is like a 3-star. Okay? Big deal. This right here is some sort of initial value. This is whatever value you had at A. Okay? A is sometimes 0, sometimes it's something else. Some sort of value that's given to you. And then what is this? You know, what did we just say it was? The amount of change, yes? So this is sort of like where you started, and then this is the amount of change, how much you change when you start at A and you go to B. So if I tell you where you start, and then I tell you how much you change, what is that going to give you?
B.
Not quite B, but half of B. This is going to tell you where you are at B. This is the value at B. Okay. Now, I could put in there f of a plus f of b minus f of a, and you've got a little more algebra there. But this concept here that I know is some kind of a starting point here, and I add to it how much it has changed, then this tells me where I am, okay? Does that make sense to everybody? Okay, putting in, this is sometimes called an initial condition. And if you're ever reading one of these problems and it just gives you this random, oh, and by the way, f of 2 equals 7. I'm pretty sure you're going to have to do this almost always, okay? It's giving you this starting point. So let's look at this from the velocity acceleration point of view. So if I give you velocity and I tell you that some point, some position was x of 2 equals 5. Okay, or when t equals 2, x equals 5. Remember, they sometimes say it that way. When t equals 2, x equals 5, they like to write it like that. So, and then I ask you to find the change in position from t equals 2 to t equals 10. Okay, here's the thing, and this is what connects these velocity acceleration problems to these general, what I call flow rate problems, rate of flow problems. Okay, if you want to find the change in something, you need the definite integral of the derivative of that. What's the rate of change of position called? Velocity. Okay, and then you would find that definite integral from 2 to 10. Then you'd look and see, well, what did they give me? Did they give me a graph, or did they give me a table of values, or did they give me a function? And you figure out how to evaluate the definite integrals. Does that make sense? Okay. If instead I asked you to find the position when t equals 10. If I said, okay, I want to know how it just changed. I want to know where it is. That's two different things. Okay? It's two different things. Where is it? Okay? So if you want to find where it is in t equals 10, you need to start with the position that you know, some kind of known value. Okay, that was given at the beginning of the problem. Okay? And then to that, you need to add how much it changes. This number needs to match that number right there. Okay? So if I gave you x of 0, that number would have to be 0. If I gave you x of 9, that number would have to be 9. Does that make sense? Okay? All right, you can do this with lots of different kinds of functions. It doesn't make any difference whether it's velocity or position. It can be for some kind of weird function like this one. I'm going to give you r of t, which is the rate of change, that's your t, of the radius of something. And I'm going to tell you that it's in centimeters per second. And there's your second clue that you're dealing with the rate of change. Okay? R of t is the rate of change of radius, and if that doesn't hit you in the face, then you'll say, oh, centimeters per second, that's the rate of change. And then I'm also going to tell you that the radius at time 0 is r, I use a small r for radius, small r for square, centimeters. So at the beginning of the problem, this radius is 3 centimeters, and I'm going to give you how it's changing. Okay? So if I asked you to find the average rate of change of the radius from t equals 0 to t equals 5. Okay? Average rate of change is the same thing as average value of the rate of change. And what's the formula for average value? 1 over b minus a times the definite integral. Yes? So 1 over 5 minus 0 times the definite integral from 0 to 5, of what? The average rate of change. Find the average rate of change of the radius. I need the function for the rate of change of the radius. So that's going to be that big R. I know it doesn't have a prime on it. They just didn't like writing prime on everything they do. And that will give me the answer. Does that make sense? Okay, if I asked you instead to find what is the radius when t equals 3? Big R doesn't tell me the radius. Big R tells me the rate of change of the radius. To go from centimeters per second to centimeters, what do you have to do? Antiderivative, okay? Antiderivative. So I'm going to have to take the antiderivative. And the other key to this is that you've got to remember, if you want to know what the value is now, you have to know where it started plus how much it changed. So out here in front, you need to have a where it started. This is the thing that people leave off, okay? So I have a where it started. Well, I don't know if it started there or not, but I have a number there. What do I have? R of 0. It started at 3. So as soon as I say R of 0 here, whatever I put right here has to go right here. And then go to wherever it is you want to be. This can work if you're going forwards or backwards. It doesn't make any difference. Okay? Can I see? Okay, that is our starting point from here. And I wrote this on the bottom of my paper. I wrote the new value equals some sort of given value or initial or given value plus the amount of change. Okay? And once again, just keeping in mind those things that have to match up. All right? Okay, so today we're going to start with some velocity acceleration problems, and this will be kind of woven in there a little bit, and then we're going to go to some that are more directly this, that are not velocity acceleration, and I promise we'll take a break in between. So pull up 2004 exam, and let's look at problem number 3. And get your calculators out. Although we may not stop and actually compute everything, we may just talk theory. I feel like y'all know how to push the right buttons on your calculator for the most part. We'll do it a little bit. Okay. I just copied a little bit of the details from that. There's a horrible function they gave you. Yes. Y'all recognize that tan -1 thing? Remember what it is? Not one of the tan. It's arctan, which is written there in the paper also. Yes, you find out where the arctan button is on your calculator. It's over the tan button. It says to untan this. Yes? Take the tan button. Okay. We maybe will push the button on here, maybe not. Okay, so I just pulled this out. And this right here, when I see this, when g equals 0, y equals -1, I like to change it into this. You don't have to do that, but those two things are the same thing. Okay? All right, question number 1. Find the acceleration of the particle at time t. Okay, so question number A says acceleration at time t. That's what it's asking you to do. Okay? So I don't want to know the answer. I want to know how do you find acceleration. Derivative of velocity. So you write that on your paper. You write, okay, Mr. Greater People, that's what I'm going to do. This is the calculator part. That's all there is to it, and then you're going to write the answer down. Y'all know how to do this on your calculator? Yes? We're not really going to stop and type. You need to get this typed in correctly. Typed in correctly. Okay? and then you need to do in derive, yes? Okay, I'm gonna put a little note here, you might wanna grab a different color to note to yourself, I didn't actually type this in, I might wanna type it in and make sure it's right. Okay, but I'm gonna give you a value here. Okay. They're not picky about rounding, so, they give you credit for either one of these answers. Not picky about rounding. Everybody knows, you understand how to do that on your calculator without us stopping to do it, yes? Okay. But you understand that sometimes that's where you mess up as well. You know what you're supposed to do, but somehow the execution doesn't come off quite right. Okay, look at question B. Okay. Is the speed increasing or decreasing? We have answered this question before. How do you determine if the speed is increasing or decreasing? Same sign or different sign of what? Acceleration and velocity, okay? So you're gonna stop and you're gonna put a little note to yourself. It's speeding up or speed is increasing. You can say either one. Speeding up if velocity and acceleration have the same sign. So write it down. And then you're gonna write it as, or put speed increasing, I guess, since that's the word that they used. That's speeding up, okay? If speed is decreasing, that is slowing down. If velocity and acceleration have opposite signs. Get it on your paper. You're gonna get a point for knowing what they've asked you to do and translating it, okay? Now you have this horrible, horrible function. Okay, but it's typed in your calculator. So then you're going to find v of 2, and you're going to determine if it's positive versus negative, okay? Do we care what it is exactly? You're just going to determine if it's positive or if it's negative, and I'm going to put this in a color here, so it turns out that it's less than 0. You're going to write that on your paper, and then you're going to determine the acceleration at time 2. Is that the question you already did? Yes? That answer's from A. So that's not unusual, okay? Oh, sorry, don't do that. Less than 0. Okay? For A. And they have the same sign, therefore, speed is increasing. And y'all know how to find v of 2. You just do a trace if you got the calculator, the graph of it, or from the home screen, go to y1 and treat y1 like a function. y1 parentheses 2. Is everybody good? Okay. Question number 3, C. Read the question. Word highest in calculus translate to the word max. Okay? So what you're asking to do is find the maximum, not the maximum velocity, but the maximum position, the maximum height. If you want to maximize y, how do you do it? I want something to be a max. What do I need to look for? Critical number. You want to see where y prime changes from positive to negative. So look for where y prime, that's the same thing as v, changes from positive to negative. Okay, you're going to look for that on a graph. You're going to set it equal to 0, find, set the velocity equal to 0, yes? Okay, that's not too bad. But look at it on a graph. I didn't draw a picture of the graph, but look at where the velocity changes from positive to negative. Yes?
Did you use y prime because it's on the y-axis?
I did.
So do you need to define it somewhere?
It's defined at the beginning of the problem, and I also defined it right here. When they gave me this, I defined it right here. Okay? All right, it never would hurt you to write one more thing, y of t equals position, that would be okay, but I think that's where they defined it up there at the top. Okay, everybody see? Okay, I'm gonna jot this answer down, this is just, y'all can go back and, get this, so let's put a note here, look at the graph. Of v, not of y, and look where v changes from positive to negative, and the answer is 0.443. On this particular one, they didn't penalize anybody for not checking endpoints. I don't know why. Maybe it's, I don't know, I'd have to look at the graph itself to see why, but sometimes they, decide not to do that. Okay, and then I want to get to the last question, because this one kind of, all of this other stuff we've kind of already done before, but this last one asks you to find the position of the particle at t equals 2. Okay, so they want you to find, let me translate that, find y of 2. And that's that thing I was just going over a minute ago. Yes? Okay, they gave me a starting point. What starting point did they give me? Y of 0. And I need to add to that an amount of change. And an amount of change is another name for a special kind of integral, definite integral, okay? The integral from where to where? From where you started to where you're going, like that. Okay? This is y. You don't put y in here. You put y prime in here. And y prime is b. Okay, where did I start? Plus how much did I change? Okay, so everybody see how that works? So then it's going to be -1 plus whatever this value is, and you'll do that by doing your function integrator on your calculator. Okay, and I don't know if that seems like it asks me another question. I'll get there in just a second. And this answer turns out to be, just for those of you who want to go practice this on your calculator, 60 or 61. Did I see something with a hand?
Well, are they using like Y for position instead of like using S or something?
Okay, so we'll do it here again. All right, never hurts to repeat things.
Well, I know that was circle, but like
Okay, but up at the top it says the position is y equals -1,
okay,
and I used that to define this as the function
okay,
because they gave it the name. But it is not unusual for them to use s.
okay. So
Okay.
that's the position.
Yes, that's a position function. In a lot of times in physics, in upper level science, when you start doing 2 dimensions, instead of using s, you use x for horizontal position and y for vertical position, because often you have to do both of them. Okay? Does that make sense, everybody? Okay, good. Now, always go back and read the questions. I don't remember what it asked me, but let's read the question one more time.
Is it particle?
Yeah, first of all, they didn't give me any units, right? Okay. And second, it says, is it moving towards the origin or away from the origin? Okay, well, I know where it is. It's at -1.3. It's over there. So is it moving this way or that way? What is that asking you to find? Well, not acceleration. Velocity. Velocity is positive if you're moving to the right. Velocity is negative if you're moving to the left. So that second question is asking you to find the velocity at that thing that you just found and determine if it's positive or negative. Does that follow? I'm standing here and they want to know if I'm going this way or that way. So if I'm going this way, my velocity is positive. This is the origin. If I'm going that way, my velocity is negative. Actually, it's up and down, but I can't do that. Okay. Okay, it's up and down. Turn your axis on its side. It would be moving up, yes, away from the origin, okay? So when you do this, you're going to get that this value is negative. Okay. Now, then you have to think it through. It is below the origin, and it is moving down. Therefore, it is moving away. You have to put the two pieces of information together. It's below the origin, instead of left and right, below the origin, and it is moving down. Therefore, it is moving away. Not because this is negative, but the combination of the two things. Okay? Towards this, right. If this number had been a positive number right here, and this number was negative, then the answer would have been moving towards the origin. Okay? All right, so that kind of reminded of a lot of things that we did with velocity acceleration before, plus this sort of new thing here that we did at the beginning of class. Yes? Okay, let's do another one. We're going to do 2005A. Well, take a look at 2004B. I'll tell you why I'm skipping it. I'll show you why.
2004B is number 3.
Yes, 2004B number 3, just so you know why I'm skipping it for right now. We actually are coming back to doing it, but take a look at that problem. Okay, do you see that it's velocity? Okay, but what is it giving you at the very beginning? A chart, a table. And what we're gonna do probably either this Thursday or the one that's after spring break is we're gonna take a look at the 5 or 6 problems that have tables, because these tend to be combination problems where there's a little bit of velocity, and I think the word Riemann sum is in here. They tend to be problems where they pull various things in, so rather than treating this as a straight velocity problem, we're gonna save this one. The ones with the table, we're gonna save and do 2 or 3 of those in a row, okay? All right, so 2005, number 5. You get to number 5, you're working on a problem that you're not allowed to use your calculator on. And notice that they didn't give you the function as a analytical function this time, they gave you the function as a graph. Okay? But it's still, they gave you velocity. If they've given you velocity, there's a good bet they're going to ask you about acceleration and about position. Something about those two things. So first, read the question. So write that down. Velocity is in meters per second. Okay? And now they've asked me, question A, to tell them this answer. First, tell me what's this answer, which we're going to do using what technique? How are we going to come up with the value for that? We've got to find a definite interval, and they gave me a graph. Area under the curve, yes? Okay, so area under the curve. So note to yourself, area. Because I have a graph. And I don't have anything written out. Okay, in fact, why don't you just find that value, interval from 0 to 24. You can either do it as a trapezoid, or you can do it as a rectangle or 2 triangles. They're at 360. Okay? All right? And it says, using correct units, explain the meaning of this. Okay, 360 what? I took meters per second and I took a definite interval. What are the units going to be? Meters. Don't miss that. When we go back and flip to that page I told you before, what does this definite interval mean? If you take the definite interval of a rate of change from 0 to 24. Change in position. We have an object, have seen this particular object here? Car. Change in position of the car from t equals 0 to t equals 24. How much the car moves, displacement, okay? If it's all positive, if this graph is all positive, it's also distance travel. If you don't have any changing of turning around and going in different directions, but it's really displacement, okay?
When you wrote change in position of car, is that you were explaining the meaning of?
Yeah, change in position, I should have set up the car in meters. In fact, if I had left that in meters off, I probably would have gotten full credit for that, because it said including units. Okay? Everybody good? All right, let's look at the second question. All right, they want you to find v prime of 4 and v prime of 20. And if it doesn't exist, you need to tell them why it doesn't exist. So v prime of 4. What does that mean? The slope of v and 4. Yes? Look at your pencil at the point where t equals 4. What's the slope right there? It's changing from one thing to another. It's a sharp turn. So does v prime of 4 exist? No, it does not exist. Now, you're going to get a point for saying it does not exist, but you need to tell them why. Okay? All right? And you said it's changing. I'm going to give it to you in calculus notation. V prime of t as t approaches 4 from the left does not equal v prime of t as t approaches 4 from the right. Y'all remember us using this v prime limit mixture? So we don't have to write the word limit. Okay? The velocity, the slope of the velocity from the left does not equal the slope of the velocity from the right. And I know y'all turned your nose up the other day when I said, some people wrote this in paragraph form. But what if you forget this notation? You could write the slope of the velocity from the left does not equal the slope of the velocity from the right in words of 4. Does that make sense? Okay, v prime of 20.
If you write it in words, you say it's
Yeah, if it's right. If the words are right. Okay, how am I going to find v prime of 20? I just need to find the slope of that line. Yes, I don't need the whole equation, I just need the slope. Okay, so the slope of that line, you've got the point 16, 20, and you've got the point 24, 0, and you're going to find the slope. Okay? That's not even calculus, right? Got negative 5 half. Are we good? Actually, I got 20 over negative 8, which is, that will also set. Okay, negative 5 half. Read it again. What else does it say? Indicate units and measure. Okay, I took velocity, which was meters per second, and I took its derivative. So what is that going to be? Meters per second. That's the generic. If you put meters per second squared, they're going to accept that. Okay? All right, question C. Oh, no. Write a piecewise function for acceleration. Okay? That's okay. Acceleration is the same thing as the derivative of velocity. Piecewise. How many pieces does the velocity function have? 3. How many pieces is the acceleration going to have? 3. And the 2 of them are super easy. Okay? Acceleration is the slope of velocity. The slope of velocity. So what's the center piece? 0. And just put your define your place, your numbers in there. This T. Okay. What's the third piece? Yeah, because we found that in part B. And all you got to do is go up and find the slope of the first piece. Okay, and put it from 0 to 4. Y'all see? Not really that bad. You know, the first time I worked this problem, I started to write the equations of those lines. So they didn't ask me to write the velocity function, they asked me to write the acceleration function. Okay? Yes, Katie?
So why did you put equals on anything?
Okay, because we just determined that v prime does not exist at 4. And where else does it not exist?
60.
Which is this point and change. Okay, so that exists. Okay, I don't know that they took off for that because it's not what they were really looking for there, and they'd already given you the point if you knew that in the first part. Not sure. All right, last question. Is not really a velocity acceleration question. It's just a calculus question that's put into a velocity acceleration problem. Find the average rate of change of v. How do you find the average rate of change of anything? 1 over. This b minus a is b minus a, the integral from a to 20 of whatever you've been asked to find the average of. Okay, so what do I put here? B or B prime? I want the average value of the rate of change of velocity. I put the rate of change of velocity here, okay? So what do I put here? I put B prime. Y'all see? That's a tricky little thing. You have to watch out for that language, okay? You could have put A there if you wanted to, all right? Okay, so then you go, okay, how the heck am I supposed to find that out? Well, if I take the antiderivative of the derivative, what do I get? V. Yes? Okay, so I'm going to get V evaluated from 8 to 20. Or another way to write that would be V of 20 minus V of 8. And you read those right off the graph. The tricky part to that is this right here. Is getting, if you want to, the definite interval of V prime. Okay?
Any student of a teacher or coach must report to the library now.
Okay. All right. And then you're going to get your answer to that, and I'll write the answer down for you, just so, because we kind of need to stop recording or I'll never get it saved. And they ask some other question there. Does the mean value theorem, I love it when they throw something like that. That has nothing to do with velocity or acceleration. They're throwing in a mean value theorem question into the middle of this. And we can't predict when that's going to happen. So then you have to stop and remember, what does the mean value theorem say? Okay, and I'm going to stop. I'm not going to answer that for you right now, because the focus today is on these rate of change problems. Okay, so what I'm going to do is I'm going to pause right now. I'm going to give you all an assignment, all of you, those of you listening in. Okay, I want you to go to 2000B number 3, and I want you to not work them all the way through, but jot down, like if you were working this problem, you know, write this down. And you don't have to finish it. Okay. 2000, I said 2000B?
Yeah.
Well, that's just weird. 2005, B, number 3. So I'll pause this and let them put it right in here so I'll make sure I said it right. 2005, B, number 3. Looks like the right, one of the right kind of problems? Look like a velocity problem? Okay. All right. We're going to pause for a little while.